Hello everyone. In this video we will continue to examine topic 7.3, the structure of matter, and in particular we will begin to unpack the standard model of particle physics. Alright, so at this point what we're going to do is sort of dive into the meat of the material for this topic 7.3. And it's important before we do that, though, to have sort of an understanding of what is about to come. So the standard model of particle physics is what is known as a quantum field theory, or a theory of particle physics that is based on sort of quantization, the process sort of founded in quantum mechanics in the 1920s and 30s. You end up with quantized energies, things like that, but whose fundamental ontology is related to fields. That is, it says that the most fundamental thing that exists are actually fields and not particles. We're going to talk a lot about what elementary particles are, but at its most fundamental level, this theory says that what a particle is a quantum excitation of the fundamental field. It's sort of a thing that pops out of the field when certain conditions are met. And the math underlying quantum field theory is significant. Quantum field theory is at best an advanced undergraduate level class, and more likely early graduate school. It is the kind of class that most physics majors may not even take unless you go into sort of elementary particle physics or theoretical physics writ large. And so it's important to recognize that what is about to follow is a whole bunch of description, sort of here are words that correspond to what we think exists, and here are their properties as best you need to know. But way more than in other parts of the course, there are going to be a number of times where I simply say, this is what there is. This is the way we describe it, and this is how it behaves, while giving basically zero justification for why we should believe that. Suffice it to say that we should believe that. The standard model of particle physics is unbelievably successful in both predicting and explaining a variety of microscopic phenomena. It is our most advanced and most sort of successful theory in that sense. It reduces virtually all common phenomena, everything we ordinarily encounter, to a set of fundamental interactions and particles. So in that sense, it's extremely successful, but its success will not necessarily be obvious in this topic 7.3, in part because both the experiments and the math would take us significantly beyond the bounds of this course. So way more than in other subunits, I'm simply going to say, here's what exists and here's what you need to know about them. We're going to introduce a tremendous amount of vocabulary. This is one of the few units where I would strongly advise making flashcards as we move through it to try to keep track of the different bits of terminology, and to sort of focus your attention on the patterns in these classes of things. This is a unit that is really good for saying, okay, although we don't quite have the math to handle sort of where this comes from, we can recognize the patterns in how the particles interact and what is going on. And we can actually use a set of diagrams known as Feynman diagrams to make very specific predictions about how different particles might interact. Know that even if I don't mention it, virtually every sort of section of this subtopic is undergirded by substantial experimental evidence that comes from the particle experiments done from more or less the 1930s on, all the way up to and including the LHC and the experiments done to discover the Higgs boson, which is the most recent fundamental particle discovered. We are going to discuss the standard model in detail. So this particular diagram is one that you will more or less be able to reproduce by the end of this. These are the most fundamental particles. Something that might jump out at you is that protons and neutrons and other particles that we have seen before don't necessarily exist on this chart. And in fact, there's a good reason for that. They are not elementary, which we will discuss in a bit. Note that the standard model includes both matter and antimatter, which we will get to eventually. But for now, know that for every matter particle, there is an antimatter particle with the same mass, but opposite charge and quantum numbers. We will get to that in due time.